In this video, I'm going to continue on talking about solutions to the Schrodinger equation in one dimension with the potential modeled as a harmonic oscillator. And this is the equation that we ended up with at the end of the previous video. And remember that the epsilon is proportional to energy and that the xi is proportional to the distance from the center of the potential well. And so what we want to do is start actually trying to find the solution to this psi here, this function. So this is a differential equation, and so solutions will be functions rather than just some number. And to do that, we can actually sort of start looking at what this equation will do at large values of xi. So at large xi, this xi here is going to start overpowering this epsilon here to the point where we can say that this epsilon is approximately equal to 0. So we can have so it would just be this second derivative of the function minus xi squared times the function equals 0, which we can then manipulate so that we have the second derivative of the function, which is a function of xi with respect to xi, and that will be approximately equal to the xi squared times the function of xi here. And so a solution to this equation, a solution to the equation that looks like this, will end up being, so we can say that the solution for psi as xi goes to plus or minus infinity is equal to some constant multiplied by e to the minus xi squared over 2 plus some constant times e to the minus xi squared over 2. And so this part here will go to infinity. This will go to infinity as xi goes to infinity. And so we just set a equal to 0 as one of our boundary conditions there. And this, if you remember from the previous video, I said we needed a Gaussian function. Well, this is our Gaussian function that will be part of our solution to the Schrodinger equation. And so what we can say then is that the solution to the Schrodinger equation will have a form that is, so as a function of xi, that is of the form some function here times, times our e to the minus xi squared over 2. So now we have this function here times this Gaussian function here. And so if we then plug this back into if we plug this back into our differential equation, what we have is the second derivative of our function f, which is a function of xi, times, and I'm just going to write it like this, exponent of minus xi squared over 2 And so this is what our function has now become. So that is with respect to xi. So the second derivative of our function with respect to xi plus our epsilon minus xi squared times our f of xi exp minus xi squared over 2, and that is still equal to 0. So now that we've made this substitution into our Schrodinger equation, we have this. And then if we just take the first derivative, so we're just looking at this part now. If we take the first derivative, what we end up with, so I'll just say the dx, so we'll call that the first derivative of it, is going to be equal to the exponent, so e to the minus xi squared over 2. And so this was just from using the product rule. So we have a product of this function and this Gaussian function, this exponential here. So we will end up with df of xi over d xi plus our f of xi, or f of xi, or f, no, so it should be the xi times the f of xi. So it should be, we should have a xi out here times the f of xi. And so this is the first derivative, and then we can say that the second derivative, so taking the derivative of our first derivative now, what we end up with is the exponential of minus xi squared over 2 times d2 f of xi. That looks pretty bad, but that's supposed to be a xi right there. D xi. And this is the second derivative. And then minus 2 xi times df of xi over d xi. And then plus we have our f of xi times our epsilon minus 1. I believe that's what it looks like, and then we have that equal to 0. And if you have watched my my videos on differential equations, on these special functions and differential equations, this part here in these square brackets should look kind of familiar. And so that is of the form, of the general form, d2 dy dx squared minus 2x dy dx plus lambda y equals 0. And this right here is the Hermite equation, of which solutions are the Hermite polynomials. And so I'll go through sort of quickly here how to find solutions, because there are some things that we can get from that are illuminating. So we know that this f of xi here will have solutions of the form, so I'll write that little bigger, f of xi we'll have solutions in the form of a power series. So that's A naught plus A1 Xi plus A2 Xi squared and so on, going to infinity, which we can write in shorthand as a summation from n equals 0 to infinity of a n, and then Xi to the n. And so this is what our function will look like. And so if we take the first derivative, so we'll say the dx of it, what we end up with is, because this n will come down in front and then be lowered by 1, we end up with n equal from n, the summation from n equals 0 to infinity of an, well, I forgot the n, so n, a n, and then times Xi to the n minus 1 power. And if we do the second derivative with respect to Xi, so I put x's here, but you can just know that this is with respect to Xi. We go from n equals 0 to infinity, and now we pull down an n minus 1 here, so what we end up with is n times n minus 1 an, and then we have our Xi to the n minus 2 here. And so if we then plug these summations back into our differential equation, what we end up with is the summation from n equals 0 to infinity of n times n minus 1 an times Xi to the n minus 2 Xi times the summation from n equals 0 to infinity of n times an times Xi to the n minus 1 plus the summation from n equals 0 to infinity of an times Xi to the n times epsilon minus 1, and that is equal to 0. So this was just plugging in the summations for the second derivative, the first derivative, and the function into our differential equation. And so we can then actually, by sort of shifting these n's around, get everything so that the Xi's are all multiplied by, or all to the n power. And so, well, this one will actually become that, because if we take this in, this will just become Xi to the n, but we can shift these n's around so that we end up with, and I'll just write the first term on here, so n equals 0 to infinity, because these two terms will be much the same, but we end up with n plus 2 times n plus 1 n plus 2, and then we have our Xi to the nth power, and then we will have the rest of this on here. But just by sort of shifting the n's around on this, we can get everything in terms of Xi to the nth power. And so this makes it easier for us to group the like powers of Xi, and then sort of subtract. Then we would distribute the Xi out and set all of the coefficients equal to 0, and what we would end up with is a of n plus 2 is equal to 2n plus 1 minus epsilon over n plus 2 times n plus 1, and that is multiplied by an. So we can get the an plus 2, so the coefficient 2 higher in terms of the coefficient at some level. So if we had this as a sub naught, then we could actually get a plus of 0 plus 2. So we would get a of 2. And so we can get those in turn. We can get the a2 higher in terms of this a right here. And so that's what this recursion formula is telling us. But if we take this to very large n, so if we do the summation of n of an plus 2 over an, this will behave similarly to an e to the x squared, which this will go to infinity as we get to much larger and larger. Well, if we get to much higher terms in our solution in our power series here, it will start the power series will start behaving like an e to the x squared, which will go to infinity, and we don't like infinities. And so essentially what that means is that we must have our power series terminate at some point, and then it will become a polynomial. So just a reminder, a power series is of the form a naught plus a1x plus a2x squared, going off to infinity, whereas a polynomial is of the form a naught plus a1x plus a2x squared plus, and then it terminates at some a n x to the n. So there is no power higher than this, whereas in a power series it goes off to infinity. And so we want this to terminate at some point and become a polynomial. And so we want it to get to a point where our a n plus 2 is equal to 0, which means that we have to have our 2n plus 1 minus epsilon over n plus 2 times n plus 1. We want that to be equal to 0. Well, we can't have the denominator be equal to 0 because that is dividing by 0, and so we know that we need our 2n plus 1 minus epsilon to be equal to 0. And this will happen, so we can rearrange this around, and we will end up with epsilon being equal to 2n plus 1. And so this, remember, is equivalent to our energy. So this is telling us that energy is quantized. Quantized. And so that tells us that our energy must be quantized. And so if you remember, our energy, so when we got this epsilon here, we said that our energy, and I am going to suggestively put a little n down here, is, well, we know why the n is there, because our energy is quantized because of this n right here. And so we have our quantized energy equal to our epsilon quantized. And remember our E ref, we had this multiplied by our E ref, and we said our E ref was 1/2 h bar times omega. And so we said that this E n here was 2n plus 1, and so we have 2n plus 1 times 1 half h bar omega. And so this is what we end up with. And so if we multiply this 1 half through, what we end up with is n plus 1 half times h bar omega. And this is the allowed energy values, for our quantum harmonic oscillator. So these are the allowed energy values for the quantum harmonic oscillator. And you'll notice, remember in the previous video I said that E ref was equal to the energy of ground state, and we said that the ground state energy was 1 half h bar omega. Well, we see that if we set n equal to 0, so that we have 0 plus 1 half times h bar omega, this is just 1 half h bar omega. And so that is our ground state, whereas if we had n equals 1, for instance, then we would have 1 plus 1 half times h bar omega. And so that would be equal to h bar omega plus 1 half h bar omega. And so we see that as n goes up, that this will just keep going up as a function of n. So if we had 2, it'd be 1, or it would be rather 2 plus 1 half and multiplied by h omega. And so now we just have 2 h bar omega plus 1 half h bar omega. And so this will just keep going up by integers of 1. So we can just say it kind of goes up by factors of this h bar omega here. And so that is our allowed energy values for the Schrodinger equation. I think that's where I'm going to end this video. We will continue going on in the next video. So just to give kind of a spoiler, what we're going to end up finding is, and you may have guessed this already, is that our functions, so these polynomials, so as I said, we wanted our power series to terminate and become a polynomial. Well, those polynomials are going to end up being the Hermite polynomials. So the Hermite polynomials. That's what we're going to find in the next video. There's, I mean, that's kind of the main thing we're going to find. There's a little bit of other stuff as well, but that is sort of what we're going to get to in the next video. So just to recap from this video, we ended up with this differential equation in our previous video, and we wanted to solve this for this psi that's a function of xi, where, if you remember, xi is proportional to x. And the first thing we did was look at large xi, and we essentially, we got this as a solution as xi goes to plus or minus infinity. And we wanted our xi to be a Gaussian function. So we took this right here, which will asymptotically go to 0 outside of the range of the origin. So like I said, it's a Gaussian function, so it's going to look very similar to the bell-shaped curve, and it's going to be right around the origin, and as it goes to infinity on both sides, it's going to uh, go towards 0, which will make it so that our function, when we are outside of the potential, so our potential would look like this. And so you can see it makes it so that our potential goes down towards 0, or our wave function goes down towards 0 outside of the potential. And so that's what we wanted to find as she gets very large, is for that to go down towards 0. And so we ended up with our wave function being equal to some other function that's a function of she, that's a function of position, times our Gaussian function. So we plugged that into the differential equation. We differentiated twice, and we got it in this form right here, which is the form of the Hermite equation times this Gaussian right here. And we said that it was going to have a solution that looked like a power series like this. And so then we differentiated that power series twice. We put it back into our differential equation, kind of shifted these n's around so that we could get all the she's to the n power. And from there, if we took every term from each of these, then we could set that we could end up getting this recursion formula here. But we said that this recursion, well, with this recursion formula, if we kept the power series, if we kept our function going on to infinity, that we would end up behaving like this e to the x squared power here, which goes to infinity outside, or as x goes to infinity, then the function actually goes to infinity. And so we said that this had to terminate and become a polynomial. And so we said that at some point, this a would have to become equal to 0, and for that to happen, this right here would have to be equal to 0, because the a before it that you would be multiplying this by, so the an would not be 0. So this top part had to be 0. So we said epsilon had to be equal to 2n plus 1, and that gave us our allowed energy values for the quantum harmonic oscillator. Anyway, I hope you found this video useful. I will continue and probably finish off at least what's called the analytic method of solving the one-dimensional Schrodinger equation with a potential modeled as a harmonic oscillator. I probably won't spend as much time on it, but in the video after the next one, I will probably look at what is called the algebraic approach, or maybe even sometimes the commutator approach. But I'm not going to spend as much time on that. I think the analytic approach is a little bit more intuitive, and I mean, it's the way of doing it that I prefer, but this is a valid way of doing it. So I will talk a little bit about that in a couple videos from now. Anyway, I will see you in another video.